This is lesson 2.2, electron configuration, and here are the objectives that we're going through. The electromagnetic spectrum is shown here. Now these are the short wavelengths here, and these have relatively high energy, and the long wavelengths are over here, and they are less energetic. So the electromagnetic spectrum covers all these different types of radiation here, but this unit will focus mainly between 400 and 900 or 400 over 700 nanometers. It's important that you can explain when the photon of light electromagnetic spectrum energy is coming off, and that is when the electron returns to its original level. So in some way it's excited. This could be by another photon or by electricity, and the electron will get it to an excited state, and when it returns back to its ground state, that is when it gives off a photon of specific frequency, of specific energy. And here we have an example of light that's coming off. So if you take a full continuous spectrum, which is all the light frequencies here, and then you let it go through a substance, in this case it's hydrogen, it releases these specific lines because this is representing actual electrons that are going up and going down to specific levels. So this is the light that's been emitted by the substance. If you look at it directly on and you use a diffraction grating, you're going to see that everything goes through except for those specific lines that have been emitted, and so in that case that's called an absorption spectrum. So here we have a demonstration of this. This here is a hydrogen that's been excited, so hydrogen gas that's been excited by electricity. And so what we're going to have is photons coming off and going back down, and if you look here you're going to be able to see the red line at least, and the blue line, and the other lines here were the aqua looking line, and a little bit maybe of the purple. You can see that there. And so this is what it actually represents here. It actually represents the Balmer series of light, which is light that's going back to the n equals 2. Now you have to know these, and that's detectable with your eyes. If you have light that's going back to the first level, that's going to be ultraviolet, and if you have electrons traveling back to the third energy level, well, that's going to be infrared. So you need to know that's the Pashen series, the Balmer, and then the Lyman series. So what those lines that you saw represent are photons of light of specific energy coming off as electrons are returning to the second level. So what you'll have is the red, which is of the lowest energy. That's going to be this one here, traveling back, and as you get further and further out, it's going to have more and more energy as it gets released. And so this one will represent that red line, and this will represent that aqua line, and this will represent the sort of purple lines that are coming off. So this is sort of the evidence that shows us that the electrons are traveling in stable waves, and that it's releasing, that they're of specific energy levels. Now if you use an instrument that's a little bit more accurate, that can measure the ultraviolet and infrared as well, you'll be able to read these bands as well. And so this is the one that we can actually see, and what you'll see here is something called convergence, is that these lines here, as they get further and further out, the difference between them actually gets smaller and smaller, and that's repeated 3 times, both from the infrared, and then as you get more and more energy down here, down to the ultraviolet. So what's that saying? That's saying that as the energy shells get further and further away, the difference between them is getting smaller and smaller, and there's a technical word that you need to learn to describe that, and that is convergence. Now this is just an actual diagram showing you what the actual wavelengths are released when an electron returns to the ground state and releases that photon. So the highest one you're going to see here is the longest distance. So in the Lyman series, this one here, when this electron returns back to its original ground state, that releases the shortest wavelength, that's only 94 nanometers, and then so that has the highest frequency. That's the nu, or the frequency. and we're going to use that to solve some problems. So you can work out what these lines are, and once the energy gets too great, the excitation is too much, we actually lose it. And so what we can see is that whatever the highest frequency is, the highest one that we can get, that's the point at which it can no longer stay and go back, in which we lose it. So that's the ionization energy. Here we have hydrogen again, and we could see these ones quite clearly on our crude instrumentation. You can look these up on the internet. You can also get things, all the other elements, and you can look at the stars and see what they're made of and the different planets by the emission spectrum that they release. Now, the original way that we would look at the electron configuration was in shells, which still has some relevance. We're going to expand on that, obviously. So it used to be 2, 8, 8, or even 2, 8, 18 was some ways of writing that. This is still useful for working out compound names and so forth. So now we have these really sort of more accurate ways of understanding how the shells are working. We're going to give these things names now. So the electron, these shells, general shells, are going to be called energy levels. So we have our principal energy level. There's 1, 2, 3, 4 down here, and we can work out how many electrons are actually in each of these energy levels, and the number of sublevels. So here, if for the first energy level, there's only an S sublevel, and for the second energy level, there are S and P's. This one's got S and P's and D's. The fourth one's got S, P, D, and F. Now, to work out the number of electrons in this principal energy level, you need to use this 2 equals n squared. And so for the first energy level, there's only 2 electrons here. And so if we put a 2 into here, so 2 times 2 squared, we get an 8. If we put 2 times 3 squared, that's 3 times 9 times 2. And that's 18. So you can fit a maximum of 18 electrons in the third principal energy level, and those 18 electrons are split up into sublevels, SPDs, and so there'll be 2 in the S, there'll be 6 in the P, and there'll be 10 in the D. So here we have the sublevels, just to make that a little bit clearer. Sometimes then you might see this written as PX, 2 in the PX, 2 in the PY, and 2 in the PZ orbitals. We'll look at the shapes in a second. D has 5 different shapes. Here you can see the different levels, energy levels. So you can see there's a little bit of overlap. You can see here that because of convergence that the energy levels gets closer and closer together as you get further apart. It gets a little bit more confusing over here because all the energy levels start overlapping and becoming very close to each other. Now we're going to learn how to write the electron configurations, and so we're going to have to be aware of the energy level orders of these, and we fill them up from the lowest energy first, and that's called the Aufbau principle. Now another way to remember this before we get into the more specific ways, you can just simply look at the periodic table, and all of these areas here are electrons filled up in the S sublevel. Here we have the P, and then we have the D, and then we have the F. So as we said before, you can use the periodic table to work out what the electron configuration is. The only trick is you need to realize that when you go from this 4s, you're not going to a 4d but a 3d. And as you go from the 4p to the 5s, again, you're not going from the 3d but you're going to the 4d. And so I don't recommend that you use this because you're probably going to get tricked up. So what you should do is this other way that you can write it out. So you write out all the S's here, all the P's here, all the 3's and the 4's, and then what you do here is you write 1S, then 2S2, then you increase it as you go along. So 1S2, 2S2, 2P, 3S, 3P, 3D, and then you increase it to a 4. You're not going to be asked the ones too far down over here, so you can kind of forget about the 4 after the F's. And then what you do is you can draw these parallel lines that go from the top right to the bottom left, and that will give you the correct order. You can see 1S, 2S, 2P, 1S, 2S, 2P, then there's 3S, that's the next one, and then you go down here, 3P, 4S, 3P, 4S, and that pulls you back over to here, and 3D, 4P, 3D, 4P, and then we go 5S, 4D, 5S, 4D. If you use this method, you're far less likely to get caught up on the trick that it sort of jumps around here on the transition metals. So we're going to get into writing them now. So what we do is the first number here is the principal energy level, the second letter here is the sublevel, and the little superscript here is the number of electrons. So here we have magnesium, so we've got 1s2, 2s2, so that's one electron here, electrons here, so 1, 2, 3, 4 electrons here, so 1, 2, 3, 4, then we've got the 2p6, 1, 2, 3, 4, 5, 6, and then we've got the 3s2, so that's where magnesium is, and that's how we write the electron configuration for it. Now, as I said before, I wouldn't use the periodic table here. I would use this system here, and so I go 1s2, 2s2, 2p6, 3s2, and that's how I would get to it. What we have here is them written in their different energy levels, so make sure that you've got the 4s here and make sure it occurs before the 3d. So what you basically do is just make sure it's at a lower energy level than the 3d. Interesting here is we don't have any that go above here because the electron is not able, the excited electron is not able to go back to its original ground state and release that photon or specific frequency because you've lost it. And so make sure that you've drawn these different boxes at the correct heights according to their energy level. Just to mention the Aufbau principle again, so you use that diagram to fill in the electrons from the lowest energy level first, and what I do is I just work out the total number of electrons and just count as I go along. And so for this one's sodium, and so sodium's got 11 electrons, so I just keep on adding 2, 4, 10, 11, and when I hit that 11 I stop. Now, most importantly, because this is IB, is they like to test you for the exceptions, and the two exceptions are chromium and copper. The exceptions with chromium and copper are that you don't have this 4s2 3d4, and you don't have this 3d9 4s2. Now, the reason for that I think is easiest to explain using the periodic table. And what we have here is the copper here. So the copper, instead of forming this full shell here, and the chromium also, what you'll see here is that this 4s2 electron actually pops off and goes over to here, and same with the copper, the 4s2 pops off and goes over to here. So if we're drawing this out, what you'd actually have is you'd have one electron here in that orbital, and then you've got 1, 2, 3, 4, 5 here, and here you've got 1 and you've got 10 here. Now the difference being is that they're all in single spins, and they're all pretty much completing here. So there's some sort of stability there, rather than having this incomplete sort of one with an orbital that's incomplete, and then this having this full with some mutual repulsion going on here. And same here, rather than having this sort of incomplete one here and then this complete one here with mutual repulsion going on here, it's of much less energy for that mutual repulsion electron to come off and to fill in here. Same with this mutual repulsion electron, it's much easier for that to come off and to go into here to create this 3D 4s1 and this 3d10 4s1. So it's a lower energy level. It's a way of decreasing the stress in the system, and so therefore it is less energetic and more stable, and that's why it forms. So just be aware of that, and that's the reason for it. Another way the IB loves to trick you is to give you ions. So if you've got a positive ion, what you have there is you don't have the original 11 electrons, you've actually only got 10, and so you need to make sure you get rid of that extra electron. Same with the negative ions. If you have a negative ion, then you're going to have an extra electron, so you don't actually have oxygen. That's even trickier because that's an isotope that's not even stable. It should actually be 2-. And so what you need to do is you need to make sure you've added that extra electron. And just finally, just to make that just a little bit nastier, if you've got transition metals, make sure that when you convert them to ions that you take the electrons from the 4s's first. Okay, so what you have here is titanium ion, right? You may be tempted because it may actually be written as 4s3d2. You may be tempted to get rid of the ones from the 3D. Don't think about that. Always remember this. as a rule. And so here we have a chromium 3+ ion, get rid of the 4 S's, get rid of 2 from here, once you've gotten rid of all the 4 S's. Now, because these electron configurations get so big, it's useful to just abbreviate them. So what you can do is you can just use the noble gases, and for argon it's 1s2, 2s2, 2p6, 3s2, 3p6, and you can just get rid of that and replace it with that element in brackets and just write the following from that. And the 4s and the 3ds can be rearranged both ways are correct. So here you have the periodic table, and you can ignore everything up to argon and then just start writing out the ones from here. And similarly, you can do that with the other noble gases. Just to recap now, so we have our primary energy levels that we use 2n2 to work out the total number of electrons, and these are the sublevels. The sublevels here have different numbers of orbitals, so S has 1, P has 3, D has 5, F has 7, and so in each orbital you can fit 2 electrons, so you times those by 2 to see how many electrons you can fit in there. So here's an analogy to help with that. This is basically some waves that have been formed, some standing waves, and there is one nodule here, and so what you can see is that there's a gap in here, and we're going to let that represent the s orbital. So there is a high probability that the electron will be found within that space, and you can fit 2 electrons within that area. Now, as we change the frequency there, we will find that the next stable resonating waves occur in 3 spots. We're going to let that represent the P, and again you can fit 2 electrons in each, so you can have 6. So let that represent the PX, PY, PZ. As we go forth and increase the frequency even more, this time we have a nice stable energy resonating at 5 different orbitals here, and that represents the D, so that's 10 electrons. And then lastly we'll increase it down up the frequency, and we'll have 7 orbitals, and let that represent the D. Okay, and then we just work our way back down, 5, 4, 3, 2, 1. So that's not a nice little analogy showing you how the electrons are in waves, and they're forming these resonating stable low energy levels, and how that creates these spaces. Now, a huge summary of all that is here is the main energy levels, the sublevels, the maximum number of electron pairs, so times all those by 2 the number of electrons, and so the maximum number of electrons in each of those main energy levels. Here are the shapes of the orbitals, and you can just draw these by making sort of like a dumbbell shape. It's kind of helpful too to maybe do the X, Y, Z axis as well. So that would be the X, Y, and Z. Now we're going to fill in these orbital diagrams. So we've already known the Aufbau principle as we go from the lowest to the highest. The next one that we need to know is the Hund's rule, is that you fill in all these boxes with electrons in one direction before you start filling in a box, pretty much putting 2 electrons in one orbital. And lastly is the Pauli exclusion principle, is that when you do put 2 electrons in, it must be in the opposite spin, and this balances things out to decrease the tension and lower the energy. Please make sure you are familiar with this term mutual repulsion, because that will be quite helpful in the next unit. And so that's decreasing the mutual repulsion from each other, pretty much just like magnets. Think of them as north and south. It's more stable if they're in this formation rather than repelling each other in this formation. And finally we get to some problems. Using boxes to represent orbitals, give the full electron configuration of the following atoms: lithium, fluorine, potassium, nitrogen, and oxygen. So first let's go to the periodic table and have a look at how many electrons each of these things have. And so we just quickly do that. So lithium 3, fluorine 9, potassium 19, nitrogen 7, and oxygen 8. Now I'm just going to do this once and cut and paste it. So as I mentioned before, the 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. Write that out each every time. Put the diagonal lines in there, and that's the order that we use. So lithium has 3 electrons, So the 1s will take 2 electrons, and then the 2s will take 1 electron. So lithium has 3 electrons, so I've just written up there all the s's will take 2 electrons, all the p's will take 6 electrons. And so what you have here is the 1s's will take 1, 2, and then the third one will go from an s. So I've just written 1, 2, 3, so the answer is 1s2, 2s1. We didn't draw the orbital diagrams, so you've only got the 1s and the 2s, so fill them up with a lone electron in the 2s. Moving to fluorine now, with 9 electrons, so I just count off 1, 2, 3, 4, and then I can count off another 6 electrons in the 2p. I don't quite get there, so it's going to be 2p5. So 1s2, 2s2, 2p5. I then draw the orbital diagrams with up to 2p, and then I just fill them in, putting one, when I get to the 2p, I have to put 1 in each before I put the opposite electron, which is Hund's rule. Potassium now with 19 electrons, and so I'll have 10 electrons that can go in the D's, and so I just count off 19, making sure I count off 6 in the P's. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and then we just draw the orbitals in there all the way up to 4s. Nitrogen, 7 electrons, count them up, 1s2, 2s2, 2p3, put 1 in each, so the 2p's will only have 1 electron in each. And oxygen, count off up to 8 electrons, that's 1s2, 2s2, 2p4, and so the very fourth electron goes back into the first 2px orbital. And as a final review, the Aufbau principle, lowest energy first. The Hund's rule is that you put them all, fill each orbital with 1 electron before you pair them up, and the Pauli exclusion principle is when you put them in opposite spins. This one will be covered by making sure you do the method that I showed you. Make sure you remember chromium and copper as exceptions, and as you turn them into ions, you take the electrons from the 4s's first.